Okay, I think we can get started. So, welcome everybody to this tech talk on strengthening mathematical formulations and optimization applications. Today with me, I have two of my esteemed colleagues. First of all, hailing all the way from Australia, we have Steve Edwards. Steve, say hi to everybody.
Hello, good morning. It's very early
And
here, so
then
apologies if I'm sleepy.
And then completing this triangle of maximizing time distance differences is Ed Klotz from all the way Pacific time zone, Lake Tahoe, if I'm not wrong.
That's correct.
And he's our senior mathematical optimization specialist. My name is Richard Obedik, and today, as I mentioned, we're going to be talking about strengthening formulations in optimization applications. So as per usual, when you have a questions, please go to the Q&A panel, ask them there. We can incorporate them in the presentation as much as possible. Otherwise, we'll stick around after it to answer any remaining questions. So this tech talk very much is a follow-up on the one we did about 3-4 months ago, where we talked about strengthening mathematical models. But this time we're going to go at it from the application side instead. But as it's almost tradition at this point, we want to get our brain loosened up a little bit for this topic. So I want to hit everybody up. I want to ask everybody to think about this question: do you think this is a strong model? Yes, no, or maybe. So I'm gonna give it a few moments for the results to pour in. Ed, since you seem to have a keen eye on the statistics, what do you think is the breakdown going to be?
I think it's going to be pretty much even between yes, no, and maybe. So 33.33% for each.
Okay. Steve, what does your morning coffee tell you?
Last time I got this extremely wrong. This time I'm going to guess 20, 40, 40. So
20, 40, 40.
And 40 the others.
Okay. It's somewhere in that area, let's say, but it's actually a little bit more extreme than this. So going once, going twice. Let's see whether we're at 74%. Can we make it to 75? There is a 75, and closing it now. So here's the result. Ed, you were wrong for a change.
He was pretty close, I would say.
First time ever.
So this is of course a little bit of a trick question. Some people say yes, this is strong, but the remaining part, 90% of the audience thinks it's either no or maybe. So Ed, I know that you have a particular opinion about this picture. So why didn't you share what you think?
Right. So there's two notions of model. There's a human model and there's a MIP model. And our human model is strong in the upper body, but not in the lower body. So when I see this picture, I think about a minimization MIP model that's good in the upper bound, namely the solutions it finds, but bad in the so-called dual bound that moves the lower bound on the best possible solution. And I tend to interpret a weak formulation as one where you have problems moving that dual bound upwards. So I'm in the no camp. But if you're only concerned about finding good solutions, you might say yes or maybe here. So with that, I yield back.
I still love that analogy. I think that is so awesome. Funny thing is, I had no idea about this analogy when I picked that meme. So, but when Ed said it, I was like, "This is brilliant. This is such a brilliant meme that deserves to be recognized." Anyway, so as I mentioned, this is very much a follow up on last time. So let's very quickly recap what we learned last time. So, what is a weak formulation? In the most general terms, a weak formulation is a formulation where the dual bound moves slowly. So the dual bound is when we have here a plot of in the x-axis we have time, so the time progression of a solve, and the y-axis we have the objective function value. This line here, this is the incumbent, so this is the actual solution we find, and you can see it drop nicely. Here we found the optimal solution, awesome. But then in this model we see this dual bound is just is just creeping up there, right? It's just ever so slightly closing. I mean, we could almost cut this off here, and then we would ideally want to bring this dual bond up. And this is what we would typically call a weak formulation in a classical sense, right? And so what do we do about it? Like so what, right? Okay, the formulation is weak. The most important thing when you have a weak formulation is to understand why. And the way to go about this is you compare the physical systems associated with the MIP and the LP relaxation, and there you try to spot the differences. And these differences hopefully help you uncover why this implies a weak formulation. And the other thing is it's really important to think about it both from an algebraic perspective, so using equations, as well as geometric interpretations, so visualizations, let's say, whichever gives you more insight. And in the last time we talked about several ways to address this. And this time, we're going to actually use those things in practice. And so in the next 40 minutes or so, Ed, Steve, and I will each present one application. These are real applications. These are not textbook somewhere. This is real things. And we're going to show you how the application is set up, where the weakness, identify the weakness, learn what it is, and then show how to strengthen the formulation. And the first problem, or the first application we're going to be looking at, is the facility location problem that Steve is going to tell us about. Steve, over to you.
Perfect. I'll take the reins. So I'm cheating here a little bit using a classical formulation to get into a real world problem. Let's see, you can see. You can see my screen, right?
Yes, all good.
Perfect. So as I was saying, I'm cheating here a little bit by using a classical problem to get into a real world formulation, but bear with me. So I'm going to be talking about the facility location problem. For those who don't know, we have some really nice demos on demos.gurobi.com, including the facility location. So if you're not familiar with the problem and want more of an intuition after this talk, feel free to go there and play around and see the trade-offs. But for the sake of this talk, it's quite simple to explain. The facility location problem asks the question, where should I locate my warehouses to satisfy my customer demands? So if we look at this image in the top left-hand corner, we can see that the problem can be described with respect to a bipartite graph, where you have a whole lot of customers on one side and possible facility locations on another. And the question is, which of the facilities will you open, and how do you direct your customers to which of the facilities? So for example, this middle image could be one solution where you just open one facility and have all of your customers go to that. But it might actually be cheaper, depending on the costs to open the facilities and also the costs to serve your customers, for it to be worth opening two facilities and direct your customers like so. So more specifically, so we have a set of customers J and warehouses I. If we want to describe this with respect to a mathematical model, we can have two sets of decision variables. So decision variable Y, which asks if a warehouse is open or not, and then a decision variable X, IJ, which asks is a specific arc or a specific customer warehouse pairing open or not. Then with these decision variables, we're essentially asking, we're minimizing the cost to both serve a customer to a specific warehouse, but also open a warehouse. We have to ensure that each of our customers are served in this very simplified version of the problem. So we have to make sure that each customer is linked to at least one warehouse. And we also have to ensure that a warehouse is open in order for it to serve customers. So essentially, you can't have a customer going to a warehouse location where there's no warehouse. Pretty simple. At this point, so I should point out that this is a very simplified version of the facility location problem. In real life, there's often a lot of side constraints and real world complications. But for the sake of the problem, this gives us enough to get into the meat of it. So as part of working for Gurobi, customers send us models all the time. And here's one that we worked with a customer. And I think I'm guessing it's a facility location sort of problem. And I'll explain why. But there could be any sort of crazy complications going on here. Let me explain. So this model is super interesting straight out of the box. You can see that it's got 1.5 million decision variables, binary decision variables, and less than 3,000 constraints. The root relaxation takes about 11 seconds, so pretty quick, given how many variables there are. Once you enter into the branch and bound tree, it's not great, it's not terrible, but you get some feasible solutions and it improves okay. But then it sort of just gets stuck. And this is similar to Richard in the opening, in the introduction, gets this behavior where it just kind of stalls. Visualizing this out, again, we're minimizing here. So we see that we have some incumbent solution that increases a little bit to start, but then we just get stuck, where the dual bound just never improves. The culprit here, and probably a fair few of our audience might have seen this straight on the introduction page, is this constraint, which is saying that a warehouse must be open in order for it to serve customers. And this is what we noticed in the model file, a lot of these sort of constraints. So that leads me to the point that I want to discuss in my section, so which is called disaggregation. So this is a technique where you separate a constraint into its component parts. So if we just taking a simplified version, if we have 4 decision variables here, all binary, and our constraint used to be x1 plus x2 plus x3 is less than or equal to 3y, we can convert this into x1. We can separate this out into its component parts where each of the variables is considered in its own constraint. We can see that the logic for the integer solutions is still the same. If any of the x's are 1, then y also has to be 1. If y is 0, then all of the x's have to be 0. So a question for the audience is this new formulation, so with the separating out the constraints, the variables into their own constraints, which of these variables is stronger? A, the aggregated. So this is our aggregated version. B, our disaggregated version. Or C, it depends. And I say Richard's already put the question out. Thanks.
Sorry, when I saw that you said which one is stronger, I thought that was my cue to press.
Yeah, no.
But then you explained it, so that was that. Interesting. We have good engagement this time. This is like we're already at 65%. Come on, guys. We can do this. We can do this. Come to 70. There's 70. Can we get to 75? This is I'm starting to sound like an auction guy. 80, 78. Oh, somebody changed their mind. 80%. Okay. Going once, going twice, and we're stopping it here. Before I share the results, Ed, how do you think the breakdown is going to be?
I'm going to say 20, 50, 30.
Steve, what do you think?
I'll go 10, 60, 30.
Okay, so it's similar.
Stay close to
Ed.
Ed.
Pretty good. That's pretty good.
Pretty good.
And we're sort of like a compromise between our two predictions, actually.
Yeah,
exactly. So Steve, what's going on here?
So this is a textbook example of stronger formulations. And I know that we weren't saying we're using textbook examples, but this is a case where a textbook example helped us identify something that helped a real world problem. I agree with the people that say that a disaggregated version is stronger. And I'm happy to try to convince the people who've clicked aggregated, or it depends. Can I get into that, Richard, or do you guys want to add anything?
No, go for it. Go for it. That's the whole point.
Well, I'd like to pipe in a little bit. So I agree with Steve. I would choose B as well. I think I would actually view it the opposite direction, that when you combine the 3 constraints on the receiving end of the arrow, when you combine constraints like that, you admit new solutions, so that the aggregated form, therefore, is weaker because it admits solutions in the relaxation that the disaggregated form does not. Now, if somebody wants to denote strength in terms of performance, then they can pick it depends, because you're adding more constraints. So you may take longer to solve the node LPs. But I go with B.
I agree. I actually would also go so as to far to say that strong is actually a mathematically defined term. In this sense, it has nothing to do with computational strength in terms of solving it more quickly, but it's more about mathematically, and I think that's a pretty clear example, actually.
And that's a good point. So if it's mathematically defined and proofs come up, and I found this really useful. To understand when trying to get my head around the strength of formulations. So how to prove that one formulation is stronger than the other. So if we have two circles which represent feasible regions of two formulations, so a red circle and a blue circle, to prove that the blue circle is stronger than the red, we need to do two things. So the proof always composes of two parts. You have to prove that all feasible fractional solutions to blue must also be feasible to red. So that shows that blue is in red. But then you've also got to show that there exists a fractional solution to red that is not feasible to blue. So that there's a point in red that is not in blue. And if you can do that, then you've proven that blue is stronger than red. With respect to the example that I put up originally. So the first part, proving that any feasible solution to the disaggregated constraints is feasible to the aggregated ones. To do that, this holds directly just by adding up the three inequalities. So if you add up the left-hand side and add up the right-hand side, you end up back at the aggregated constraint. So any possible solution that holds here will also clearly hold for the aggregated form. The flip side, that there exists a feasible fractional solution to the aggregated constraint that violates the disaggregated constraint, you really just got to go hunting. So in this case, I've picked a solution that I was pretty confident would break it. You can see that it holds for the aggregated constraint. So you just add the values. It holds for two of the disaggregated constraints, but it clearly violates the third. So we can see that for the disaggregated formulation, this would be an infeasible fractional solution, but it would be feasible for the aggregated form.
Sorry, Steve. Ed, you have a question.
Yeah, you have to go hunting, but to me, that 3 coefficient multiplying the y in the right-hand side of the aggregated constraint really screams out to be the first place to look and think about it, because to me that says set y to 1/3.
Yep.
So anyways, that's all I had to say.
That's fair.
Yeah, no, that's a good point. I didn't really have to hunt far. I didn't have to look far in this case. Cool. So what we did here is we've had the customer model. We wrote a little script that converted all the aggregated constraints into its disaggregated form, and we just went to rerun the log and see what happens. Already remarkable difference. You went from 2,000 constraints to 1.5 million. So we're looking at a very different problem now. The linear relaxation takes a very long time to solve. So not very long, 150 odd seconds. So what was it, 10 seconds? So 15 times slower to solve the root relaxation. But then once you enter the branch and bound logs, or it doesn't even branch, the incumbent crashes down. You have a really nice tight bound that barely needs to improve, and you get to optimal within 4 minutes compared to 60% gap after 10 minutes. Visualizing this out, it's a pretty interesting story. So again, we're minimizing. You have this time where you're just solving the root relaxation where nothing really happens. So you pay the price for the tighter relaxation for this time of the root relaxation. The incumbent wasn't as good to start with. But once the bound is tightened, then the incumbent comes crashing down so much that you kind of prove optimality straight away, as opposed to the vastly different behavior of the aggregated form. So it's not a cool, it's clear it's better in this case, but you could imagine cases where the root relaxation might take forever to solve, or that's mainly the price you pay. So benefits and limitations. The disaggregated model has the same number of variables, but a lot more constraints. And that's something we have to keep in mind. These constraints will normally mean that the linear relaxation, so the root relaxation, will take a lot longer to solve. Hopefully the result of that, though, is that you get a tighter bound. And this tighter bound isn't just useful as for the bound itself, but it can be very useful to help guide heuristics to find better incumbents, which is the case in this example as well. So when to use disaggregation, if you want the optimal solution, you can afford to wait a little bit longer, you don't need feasible straight away, then experimenting by disaggregating your constraints is worthwhile. Also, that you have to have constraints that can be disaggregated. That's probably a big point. If you need feasible solutions super quickly, like within seconds, and sometimes aggregated form is the way to go because you pass over this long root relaxation phase. Disaggregating all of your constraints doesn't always work depending on the objective and a lot of the other problem structure. And by work, I mean this performance where you get a much stronger bound. Sometimes you can just add a lot more constraints and it actually slows down the node throughput in your branch and bound logs. The disaggregated constraints are really just cuts to the aggregated model. And the reason why Gurobi adds a lot of cuts during its solving procedure, and we can detect these constraints. But as you can see in this example, I don't think we would ever add 1.5 million cuts for a model with 3,000 constraints. So overriding our logic and doing this yourself is something to keep in mind. And also this was one example where it helped with custom models, but we've got at least 3 where we get this completely disaggregate the constraints and resulting in just crazy good speed ups. So it's definitely a trick that I look out for now after having success in the past with that.
Thank you, Steve. We actually have a question here that I think might be worth taking right now, which is, can pre-solve aggregate rows in an attempt to make the model smaller and inadvertently weaken the model again?
Sure. Yeah, so that's a good example because pre-solve does try to reduce the number of constraints in rows, but at the same time, I don't think we'd ever try to make it weaker. So theoretically, yes, I don't believe we do, but Ed will be able to.
I do not think we allow ourselves to do that. Because the problem is when you aggregate rows, if you remove the original rows, you actually are changing the model and admitting solutions that are not feasible. Now, what we will do is aggregate constraints to try to recognize something that enables us to tighten it. This is actually the foundation of mixed integer rounding cuts. But I think at some level we do that in pre-solve. But there, again, we never throw out the original constraints that we aggregated. So there's no danger of ever weakening the model. For those of you who have asked other questions, they seem to be more general and not specific to the model at hand. So we'll answer those at the end of the presentation.
Perfect. Okay, I'll stop sharing. I think,
thanks, Steve.
And throw it to Rich.
So this was the facility location problem that we just saw, and now we're going to go to an application that is very dear to my heart because I worked on this application for 3 years. So in my previous job, I was a software developer for optimization applications at an offshore wind company, and this was one of the problems that I was working on. And so again, as with Steve's problems, what I'm presenting here is only a small part of it, but it might be a part that is relatively interesting. And there's also a demo for this available on our website, so I recommend you to check it out if you haven't already. So what's the problem here? What are we trying to do? So the question is, you have an offshore wind farm. So these are big turbines standing in the water producing electricity. But how does that electricity get to your home? Or specifically, more even better, let's go actually back to this picture, from the water out here all the way to shore. And so you have to put cables, right, to transport the electricity. And the question is, in this particular problem, between which turbines should you put the cables such that you minimize the cost? And you have, of course, you have a few constraints. So the logic is which turbines O and D should be connected, and with which cable C. So each cables have different characteristics, mainly that they have different allow for maximum power to go through them, and then how much power flows through the connection. So you have, if you have a connection between O and D, how much power can there flow? And we have a couple of considerations to make. First of all, just with Steve's example, we have to make sure that all turbines, all turbines are connected, so have an outgoing cable. So this is like every customer has to have a connection to a factory. Every turbine has to have a connection to another one where it can send its electricity to. The second one is you want to make sure that you ensure your flow balance, which means that everything that flows out of the turbine, so this for a given turbine T, everything that flows out of it is everything that flows into it plus the power it produces. So think of it like 10 megawatt turbine, so this thing would produce 10 megawatt. And then finally, you have a cable size. So in this particular case, we want to respect the cable size. So a cable has a particular rating that it cannot exceed. So the flow that goes through from O to D has to be less or equal than the sum over all cable types times the maximum rating. So always only one of these will ever be 1. And so that's how you can respect this. And to give you an idea of how this flow logic is always a little bit cumbersome, so just put that visually. So if we look at the flow balance for this node 3, we have everything that goes into that leaves node 3, so going to 1, going to 2, and going to O is equals to everything that goes into it plus the production. All right, so now you understand you have a flow network, you have some logic on top of it, some sugar to select which arcs you wanna go with. And so now we implement this. And it's not going great. I mean, if we look at this, if I just gave you this initial snippet of log file, you probably would be like, this is super nice. I mean, 500 rows, 500 constraints, less than 2,000 variables, less than 5,000 non-zeros. I mean, this is a darling of a model. Numerics are beautiful. But then, and by the way, root relaxation, LP relaxation, beautiful, 0.01 seconds. And then you start, and okay, it drops to 8% or whatever. And then it goes and it goes. This, by the way, no new solution was found. And then we're at 1,000 seconds. There I deleted some stuff because now we're at 20,000 seconds. And still same solution. And this has not really gotten better. And then I killed the run because I was like, this is not going anywhere. And if we look at this afterwards, we've explored 24 million nodes and we have done 1.4 billion simplex iterations, and we're still not at optimality. So this is pretty terrible, right? And so when we look at this visually, it even shows, right? We have here a logarithmic axis of time. And I mean, this is just not pretty to look at. All right. So the last solution is found after 25 seconds, and this just goes on. So my question to the audience now that you see this is really a small model. This goes to infinity and beyond. Which one of these 3 that I talked about, all turbines connected, ensure flow balance, or respect cable limit, which ones of these do you think is the constraint, the main culprit for the weak formulation in this particular model? So I'm launching this now. Let's see what people have to say. Steve, I'm going to put you, even I know it's early for you, I'm sorry, but
no, good.
So what do you think is the breakdown going to be this time?
I just can't believe that this is a log scale. Like it's a crazy, it's a crazy performance. The breakdown. So the breakdown, I'm going to go 20, what's that? 60.
Okay. By the way, one thing that is funny about this one is that for the audience, if you ever have an argument with somebody and there's an argument around how model size would predict solvability.
Oh yeah.
This is a great example to say no. Right? I mean, you can have, if 500 constraints is something that's easy. right? But no, it's not. So that's that. Ed, what do you think?
I'm going to say 25, 25, 50.
Okay. So I'm going to go once with 72%. People are a little bit more hesitant. I think it is a complicated question to throw at you right out of nowhere.
Yeah.
But it is really, this is really the key to what we're talking about today. Really understanding why would one of these be a problem? Why would A be a problem? Why would B be a problem? Why would C be a problem? A problem, I mean, make the formulation weak. So now it's 73%. Okay, we're going to go once, going to go twice, and we're calling it there. So we're having Steve pretty correct, actually. I mean, that's 15, 26, and 59. And so what's the answer? Well, the answer is actually, the majority is correct, but with a twist. So this is actually a hidden mixed integer rounding cut situation. So what we have here is we are saying the flow has to be less or equal than the cable limit. And this is the part which is the algebraic component. When we mentioned at the beginning, we should look at it algebraically and visually. This is the algebraic component. So here we have the equation. We say the flow is less or equal than this, but our flow only can increment by P, right? So it's in discrete values of P in this model. And so there is really, if you look at it visually, suppose we go back to this example of the turbine number 3. We have one P coming in here, another P coming in here, and then there's one being produced. So 3 are going to leave. But you can see it's multiples of 3 that we deal with. And if you look at this visually from the cable perspective, imagine this is your cable, this one right here. Let's actually change the color to something a bit more emphatic, like orange. Then what happens is that we not only going to have we're going to be able to put them into the cable, but we have this extra part over here that is empty, right? Because we can't fit another turbine, another P here, another power element, let's say. But what happens in the solver is that the solver frenetically tries to close this gap by branching itself to death with 24 million nodes, right? And so what is the obvious solution to this problem? Well, you round. So all you do is you sum over all the P's like just here, but you take the floor when you divide and you multiply it by P. All this does basically is that you round to the nearest, to the lowest P in discrete values. And so now this sounds a little bit abstract. So let's look at an example. So let's go to the example where we have 10 megawatt produced per turbine. And then we have this constraint. This actually comes from the model, straight from the model. So here you have the flow is less or equal than 32 plus 44 plus 58. So if we now round this, 32 becomes 30, 44 becomes 40, and 58 becomes 50. And so visually what this means is we have these different cable thicknesses, and these just get adjusted to just fit the power they need to convey in order to meet the turbine production. And this actually has the following result. This is then the strengthened formulation. So you go from up here to down here. And now I ask you, we're just tightening, we're just rounding. How big of an effect can this have? Well, quite a bit. So this is the result. And again, this is log scale. So let's look at this. We start off much nicer. And then after 17 seconds, we're done. So after 5 seconds, we found the optimal solution, which here took 25 seconds, but that's okay. But you can see how the dual bound is just so much nice and just closes nice and easy. So this is much more, if I told you that a model with 500 constraints and 2,000 variables would take 17 seconds, you'd be like, well, yeah, that sounds about right? For those mistaken considerations of size versus performance. And this just happened because we tightened the formulation. And this is really the key here, that it's obvious once you have created the explanation then finding the idea of rounding this is easy. But without knowing this, it's almost impossible to know, and Gurobi doesn't know, that it should tighten precisely this because it always comes in these increments of P. So this is an actual application. This is actually something that you can run and build to create cabling for offshore wind turbines. Okay, and then one question, I already saw it now, but I also I get this when I present this problem, is that what happens if P isn't constant? We have multiple forms of P, etc. Then this doesn't work anymore, right? So if you were to, for example, implement this, say you take this and you implement this strengthening in your code, right? You say, well, always round, and then suddenly your wind farm developer says, you know what, I want to build 2 different turbines in my park. I want to have one that has 10 megawatt and I want to have one that has 12 megawatt. Then this rounding will be different because you can only go by the smallest common denominator. So this really is based on a specific idea. Now, all wind turbines in the world that I know of, at least, have the same wind turbine, same rating, because they want to have consolidated logistics, etc. But still, you have to be clear about, if you get this wrong, or if something changes in your business logic, this tightening can create problems, right? But for as long as it doesn't, it helps you to bring your model down from infinity to 17 seconds. Okay, so this was my example for now. Are there any other questions that Ed, that you saw that might be worth answering right now?
Yeah, let's focus on one that is about this example. He asks, in the wind problem, would network robustness requirements be built into the formulation, and would doing so affect the strength or weakness?
What specifically does network robustness requirements mean?
I think our questioner will have to answer that.
Because I mean, there is the idea of, there is, for example, a notion. This is some things that has been investigated a few times in the literature. Is that if we go back to our original problem, what happens if we don't? No, I have to scroll the way up. What happens if we don't only do this, but we actually also allow, for example, these what's called backlinks, right? That way, if a cable fails, you still have a way to get the power out another way. That's sometimes what's called robustness. Yeah, exactly. That's what he says. One cable breaks. That's a consideration, but it's a whole nother animal. And that would very much not go into the direction of this talk. I mean, if you're really, really interested, drop me an email, my last name at gurobi.com, and then we can talk about it. But their strengthening doesn't play a role anymore. That's just a whole different way of approaching that. Okay. So if there's no other questions, then at this point, I would hand over to Ed. Ed, over to you.
Okay, there are other questions, but I think they are sort of more general. So we will handle them at the end of the tech talk. So I'm hoping my screen is visible at this point.
Yes, all good.
Okay, good. So let's do one more example, and this is going to be about lot sizing. And one thing in general, when trying to understand models, try to avoid is to just dive in directly to the most general formulation of the model, where you immediately get hit with maybe subscripts of 4 different indices, and all sorts of complicated things. I'd rather start simply with sort of the most fundamental activity in the model and then work my way up. And in the case of lot sizing, that involves really a single product. And today our product of choice is going to be something we can all relate to, which is donuts. As to whether that relationship is love or hate, that's a discussion for another time. But let's dive in and think about sort of the basic operation of a lot sizing model. Excuse me. So you have a collection of time periods And in a given time period, you have some demand for your product. Then you have the ability to produce that product through some sort of machine that you can turn on. And turning it on involves some sort of costs, typically operation costs. You also frequently have available inventory from the previous time period, so you can use that to satisfy demand as well. You also have the option of taking some of the production and preceding inventory and moving it forward to future inventory. Now, in general, lot sizing models can get way more complex than this. You can have perishable inventory, which imposes some sort of time window on the inventory. You can have back ordering, where you can satisfy an order now but not deliver it till later, and numerous other things. But let's stay away from that. Let's keep it simple and just look at the basic operation, and it will turn out that we can figure out some tightenings of the model at hand. So in terms of translating this visualization of the model into constraints, there really are two. There's the fundamental balance of flow that says that what you produce in this time period plus the inventory you have available in this time period has to equal the demand plus any product that you push forward as inventory to the next time period. And then you have some sort of controlling constraint over the turning on the machine, where you create a new binary variable u for the machine and the time period. You multiply it by some value m that is some sort of bound on production. And then what you see is that if production is positive, this is going to force you to turn on the machine. And then you will have some cost associated with this binary variable u. Okay, so let's look at a MIP model that has this characteristic. It's currently listed as hard on MIP 217, but it's about to be demoted because Gurobi 9.5 solved it within an hour, which is the borderline between a model being called hard and easy. And Gurobi's come a long way in 10 years. The MIP site says that it took 1.3 days to solve with Gurobi 4.6. It did not say the machine on which it is run. So some of the gains may have come from the fact that we ran our recent test on a faster machine. I'm not going to dig into the node log in detail. Richard already did a great job of that. I just want to point out that, like his model, this model is very small in size, and the node LPs solve very quickly. I think we can just skip to the GRB log tools plot to see what the challenge is. And again, you have this situation that is now becoming a trend here in these examples, which is that you find the optimal solution very quickly, and then you have this long tail where the dual bound moves very slowly, suggesting that there's a real opportunity, if you can get the dual bound to move faster, that we could say cut the time in half, or maybe cut it down to a quarter of the current time, if we could make the dual bound go faster here. All right, so drawing on what we learned from the previous tech talk, the key here is to figure out where the weakness lies in the formulation. So the model has 16 time periods. And again, we have this fundamental flow balance constraint. And I'm showing a snippet of the LP file of the model for a single product number 1, and the 16 time periods that illustrates the flow balance. And then we have our machine on-off constraints. And I, again, am showing a snippet here. Now, for some reason, the modeler implemented it in a bit more complex way. He or she introduced a new continuous y variable with bounds 0 and 1 and multiplied it by 480 and then connected it to the binary u variable for the same for the machine and the current time period, where the machine is associated with the product, which has label 0, 1 in this case. These y variables are essentially intermediate, so we can remove them, which is what Gurobi's presolve does. So let's just focus on the simpler constraint with the y variables removed, which fits our machine on-off condition here. I can only guess that they introduced the y variables for some form of accounting or measuring, but to a certain extent, they are not relevant. So we've got the basic activities. The next step is to figure out, why can't we do nothing? Okay, we're minimizing costs. So why can't we achieve a cost of 0? And the answer to that lies in the conservation of flow constraints. And here I'm showing it again for a single product, but this time all 16 time periods. Excuse me. And what we see here is that because the model is such that all initial inventories are 0, if you look in the LP file, the initial inventory, which is given by this variable, is not set or allowed. I guess it can take a positive value, but there's no benefit to doing so. So positive demand requires positive production. So when we start seeing positive demand, like here in time period 7 and beyond, the only way we can do that is by producing something. So we have to set some X variables, which are the production variables, to positive values. So we can't do nothing. And once we have to produce something, we have to incur the operating costs of the machines that allow us to do that production. So let's drill down to just the first 7 time periods here, where the 7th time period is the first one where we have to produce something. And what we see here is there's a lot of cancellation between the inventory variables in a given time period. So for a given time period, an inventory variable is has a flow in for one time period and a flow out for the next time period. So in other words, the inventory we push forward for time period T is the inventory we receive in the next time period T plus 1. So that results in a lot of cancellation. And when we add up these constraints, what we see is that the sum of the 7 production variables for this product 0, 1, minus the last period inventory, which is essentially now a slack variable, is equal to 3. So we need to produce at least 3 of product 1 in time periods 1 through 7. There's no initial inventory. So we have to accomplish that by setting the sum of the 7 production variables associated with the time period to be at least 3, and then combining that with our fixed charge constraints on the operation of the machine, we get that this value 3 is less than or equal to 480 times the sum of the 7 binary variables for the 7 time periods for the machine that allows us to produce this particular product. Okay, so in other words, the machine, at least one machine has to be turned on. And now we can draw on what we talked earlier at the beginning of the presentation about this notion of distinguishing the system associated with the MIP model and the system associated with the LP model. So in the MIP case, this is telling us that the sum of these 7 fixed charge binaries is at least 1. In the LP case, though, it just says that the sum of these 7 fixed charge binaries, moving the 480 onto the other side of the constraint, is at least 1/160th. Now, here's a little snippet of the objective. And what we see here is that these fixed charges are actually quite large, especially relative to the inventory costs. We can also visualize this. Our MIP model says we have this production machine, and if we turn it on, we can produce the amount of product that it's capable of doing. But when we relax integrality, what we essentially have is a tiny replica of this machine that, its energy consumption is a tiny fraction of that of the original machine. But yet somehow, despite that much lower operational cost associated with this much lower energy consumption, it still manages to produce just as much product. And that's where we have this notion of a disconnect, that the LP model is just totally unrealistic, and that's the sign of a weak formulation. And if you apply the same reasoning across all 16 time periods, you get a total production of 28 rather than 3, but it's still basically the same. It's just that you get a slightly larger fraction of 7/120 in the LP model. So the only difference is now the replica of the production machine is slightly bigger. Fundamentally, you still have the same weakness in the formulation. All right, so we found the weakness in the formulation. How do we go about strengthening it? So the previous slides raise a question, which is, where does this value of 480, which resulted in that tiny fraction, come from? So that's what the last few slides, that's the weakness that we identified sort of points us or guides us towards looking at this value of 480 and saying, all right, what's the story behind this? And if we think about it, what it turns out is, okay, we have 16 periods in the model. And if you look at the individual production data in the model, you find that the maximum demand that ever shows up in a single time period for any product is 30. So 16 times 30 is 480. And in doing that examination, what we discover is that this 30 is basically a worst case estimate that is never realized in the model data, since all the objective coefficients are non-negative. In other words, there's no reason to have there's no reward for having inventory at the end of the process. That's why the non-negativity of the coefficients is relevant here. If we could get rewarded for having leftover inventory at the end of the process, this approach would no longer hold. But there's no benefit to having inventory on hand in the final time period. And can we use that information to tighten the coefficient of 480 in the fixed cost constraints? So let's again drill down to a single product, and let's just look at, without loss of generality, the last 3 time periods of 16 time periods in the model. So when we get to this 14th time period, all preceding production has already been met. So we don't need, it doesn't matter how we got here. We've already met that production. That's the nature of the model. So what this is telling us is we need to produce 7 units in time periods 14 to 16, 2 units in 15 to 16, and 2 in period 16. Okay, that is so much less than this worst case scenario. We can just use those values instead. So instead of the 480 coefficients, we change them to 7, 2, and 2 respectively. And that's totally, that's a totally legitimate change in formulation. We're not losing any meaningful integer feasible solutions. We may be losing some really bad ones, but that's really not relevant for optimizing the model. Okay, so with that description, one more question for the road here. So the question is, did we remove integer feasible solutions with this strengthening?
Didn't you kind of give the answer away already?
Maybe. It depends.
This is good. All right, let's see. We're at 50%. Let's see how this turns out. Oh, you're gonna like this one. We're at 65. So Steve, what last time you won the guessing game? So what's your guess this time?
Yeah, I've been on a roll. I'm gonna go 50, 20, 30.
I'm
Okay.
gonna go 70, 10, 20.
Okay. We're at 70%. So let's see. 71. In the interest of time, I'm gonna close it here in 3, 2, 1. Closed. So the results are different, let's say.
Whoa.
Okay.
So yes and no are pretty equal at 39 and 46%, and then 15% say it depends. So Ed, what's the answer? And mind the time.
We've removed solutions, but they're not relevant solutions. Okay. You can still, so for example, you can produce 30 in all 16 time periods. Okay. That's a feasible solution to the original model that we have removed. But the point is, you would never do that. The nature of the objective is such that that solution can never be optimal. So this is a tightening based on the objective function. And as Richard discussed, and I think maybe even Stephen in his example also discussed, there could be changes in the model. In this case, if you were rewarded for having inventory in the last time period, you would have to rethink this. I think you could still tighten the 480, but you would need to account for that allowable inventory to push forward. So with that, I'm going to stop there since we want to see how this did and then move to our conclusions. So just visually, what this says is by tightening it, we made the production machine much more closely connected to the real production machine than it was before. And not surprisingly, this did help. And we see this here. We cut the time a little bit more than in half, but it still remains, there's still this tail after the optimal solution is found. So perhaps there is more to be done here, and we can do even better than we did in this example so far. And with that, I'm going to stop sharing and pass it back to Richard for our conclusions.
Thank you very much. Okay, final slide from my side, or from us. So what we learned today. The first thing is really creating reformulations is easy, and it happens often. And especially it happens when it's the most natural way to think about the problem. Then you just write them like this, and that's okay. That's fine. That happens. This is not a bad thing, you know? But when you identify that you have a weak formulation at hand, then it's really worth digging deep and understanding what's going on. Why is this thing weak? And then once you understand this, then you can start strengthening. But you need to understand that first. And by that fundamental approach is really the most elegant way, really, to make your model perform better, because it really shows how deeply you understand a particular problem and how, the intricacies around it. Most important thing, and this is Ed, I think, showed this very nicely, this disconnect between LP relaxation and MIP formulation, both visually and algebraically. And then finally, and this is the last words of caution to leave you with, really take care. When you make a change to the model, you need to recheck when does it apply, when does it no longer apply. And you have to also think that it may delay the discovery of potentially good or optimal solutions, as was the case with Steve. So with that being said, we just talked about donuts. So I'm going to have mine now. And thank you all for attending. And we're going to stick around and answer some questions. Ed, do you have any final words?
Yes. Don't be too worried if your initial formulation is weak. I think the right workflow is create your first formulation, give it to Gurobi, and see how Gurobi does. Because a lot of times the defaults, or maybe Gurobi with a little bit of performance tuning and parameters, will be all you need despite the weakness. What we discussed today is, what do you do when that doesn't work? And we tried to give you sort of an organized approach towards handling that case. Because even though the case of weak formulations being a problem is probably in the minority of models out there, once it happens, if you're not focused and organized, you can spend a lot of time trying to sort things out. So with that, I think I'm done, and it's time for my donut.
Steve, do you have any final remarks?
Yeah, just one to, all three of the examples came from large coefficients to our variables in the coefficient matrix. So that's often a good place to start to look when dealing with weak formulations. Ed dealt with them by looking at the objective. Richard dealt by looking at problem structure involving combinations with other constraints. I completely disaggregated them out. So that's really kind of the first place to start digging. But with that said, you can do a lot more. There's like changing variable definitions. We're really scraping the surface here with ways to strengthen these formulations. But I think ending on Ed's note of the fact that a model is good enough if it serves your purpose, and that a lot of time can go into digging and looking for stronger formulations where you might not actually need to. So with that, I will have my donut and join for questions.
Thanks, everybody. I hope you will forgive us for our love for donuts. If anybody has a mixed relationship with them.
Okay. For those of you who can stick around, we will go through the remaining questions.
Yes. So actually, we have a question. Since the very beginning, Mark asked this one. And I want to give a shout out to Mark, because he's one of the only people who's been at all tech talks we have had. So a question from him is there any special guidance you can give for MIPS where all binary variables are binary?
Leave that to Ed.
Okay, I just finished my donut, so yeah, I'm ready to go. Yeah, I think there's a couple things. So first, let's talk about Gurobi parameters. So when all variables are binary, there are a few specific types of cuts that are designed specifically for all binaries. So those would be 0 half cuts, cleat cuts, and cover cuts. And anybody else jump in if I've forgotten any, but I think those are the main three. So look at raising the intensity of those. And then if that's not enough, I think the next step is in my experience, most models with all binary variables have some fundamental underlying graph structure. And very often, well, for starters, the most sort of well-known one is the so-called conflict graph, which is how Gurobi generates its clique cuts. It basically creates a graph, finds some cliques, and those are cuts. And there are other sort of less common graphs and less common things you can compute on graphs that you may need to do specific to your model that will help you further tighten the formulation. So those would be my two pieces of advice specifically.
I would actually add one more piece of advice, which is that one thing I've come across with BLP, with binary linear programs, is that when so because it's only it's all 1 zeros, it's really interesting to think about what are the things you actually can pre-compute versus what are the things you actually have to keep in the model. Because the moment everything is binary, it's either on or off, right? So you can, for example, think, do you have any calculations where you have a complex algebra going on? If it can be either 0 or 1, does that allow you to deduce already that, for example, certain branches will never be, certain calculations will never be done, therefore you can avoid that part of the model. So the fact that you have logic allows you to create certain pre-computations, and sometimes, and those can be really powerful because it reduces the scope of the optimization. One question for you, Steve. How big was the solved facility location problem? Just quickly.
I didn't see that one. So this one had 1.5 million variables and 3,000 constraints. So if it is exactly the model we were looking at, that's 1.5, basically 1.5 million pairings of, so 3,000 warehouses, 1.5 million pairings of warehouses to customers.
So, yeah, okay.
So I guess big, not. I imagine they could get bigger with
yeah,
the number of customers. There was one interesting one, and I guess it relates to the binary question. Does disaggregation matter when constraints are equality? So in this case, if you have all of your x's equals to some big value equal to y, and it's an equality sign, then all of your variables have to take the same value all the time. So this is, I guess, relates to Richard's question, a point about if you've got these binary variables, then things might collapse down. For aggregated equality constraints, then they all just become one variable. Do we pick that up in pre-solve? I would think so, but I'm not sure. It's a good question.
By the way, my one of our colleagues, Juan, he's also attending this talk, and he wrote in the chat that lift and project cuts might also be very important for integer linear programs. Just as a side note as well. Ed, do you have any question that smiles at you?
Yeah, I want to answer a specific one to the lot sizing example I gave. So the question is, would a Gomery mixed integer cut take care of this issue since it would round 3/480 up? So I'm going to share my screen if you don't mind. If you let me.
Go for it. Go for it.
So let me try it. Okay. And let me go back to one particular slide that is relevant. So can you see it now? So
yes.
We can do it either with the 28. Well, let's go back one. Whoops. Sorry. Let's go back to the original one. So you're right that this is a mixed integer rounding cut, and Gurobi will figure it out. And in fact, it already figured it out on this problem. But that was not enough to get the 2x performance boost, because yes, this does address the particular weakness in the formulation here, but it doesn't address the issue we have with these 480 coefficients. And that cannot be done through a mixed integer rounding cut. Mixed integer rounding cuts are globally valid cuts based on the primal feasible region. The argument here was based on the objective. So you had a good observation, and you're right that in general, that notion of combining constraints and then doing mixed integer rounding can help. There's always a chance that you can come up with a combination of constraints for mixed integer rounding that Gurobi misses. But in this particular case, Gurobi did not miss it. So with that, I will stop sharing and we can move on to the next question.
So I have one I want to answer, because I think this is a recurring theme in a couple of other ones, which is how much time does it need for a consultant team to strengthen a weak model? And so I want to take a first stab at this, but then I guess Steve especially also has an opinion on this one. So the thing is, first of all, you never know whether you can strengthen the formulation. There are certain problems where you don't know how to strengthen them. It's like it's not clear. Sometimes you know you can't strengthen them because that's literally what it is, and the LP relaxation is just bad, and it just takes a long time to close. So there is no time frame. It all comes down to sitting down and understanding and what's going on, and then hopefully you have an idea how to mitigate the issue. And the other thing is, and this is something that Ed said, that you cannot underestimate. Look at the difference between Gurobi 4.6 and the Gurobi 9.5. The difference is amazing. So the solver will do a lot of work for you. So always try to stay close to the business logic and formulate that. And if it happens to be weak, then try to find a trick, try to find a reformulation. But there is no time frame for this. There is no. This is work. This is mathematics. This is relatively serious. So can take a few minutes, can take a few hours, can take a few days, can take a few weeks, can take a few years, depending on how hard it is and how complicated and convoluted things are. I don't know, Steve,
well
Ed, do you have?
No, well said. And this is like an ABC. It depends. This is definitely it depends. There's normally like 2 or 3 things you can try to tighten straight off the bat, but like take Ed's last example where he proved it and there still looks to be a weakness. Finding this way to strengthen that could take years. It might not even be possible. So yeah, it really depends.
Yeah, but I think my final comment in the conclusion is that's part of what motivated this tech talk, is to try to give you sort of a generic strategy for how to go about it. I still remember in high school and college math days, far too often when I was dealing with some hard problem, I was sort of waiting for divine intervention to strike and just give me the answer. And it doesn't work that way. You have to sort of say, okay, we're not getting what we need here. I need a strategy. I need some things to do. And that's what we were trying to communicate today, rather than sort of haphazardly trying some things and hoping that somehow something works. That's a good way to make it take longer rather than shorter.
Indeed. So this is an interesting one for you, Steve. What if we have both the aggregated and disaggregated constraints in the formulation? Will it affect the solution time?
So affect the solution time. So interesting. So I guess you could do, it's a great idea. One, best of both worlds. If you can run them in parallel, why not? If you can run aggregated, get a feasible solution, seed it into the disaggregated one, sure. In the case we're looking at, the feasibility improved so rapidly after the linear relaxation was solved that I don't think it really matters. But in general, I think it's not a bad idea. I saw there was another question about whether disaggregation always works for this problem. And the answer on that is no. I'm playing around with some random generator data. Gurobi would often outperform the completely disaggregated way. So in the cases where there's two formulations and you can't decide which one's better, then running them in parallel or running the aggregated to seed into the disaggregated might be a clever way to approach this. Ed, did you want to add anything to that?
Yeah, I think it depends is definitely relevant here. It can go either way. On the one hand, an aggregated constraint can somehow enable Gurobi to figure things out about the model that it wouldn't otherwise detect. So that's a positive. On the downside, it's conceivable that it could slow down the rate at which you solve the node relaxations, in which case that would be a negative. And then the last thing, and I actually encountered this with a couple of my colleagues here this week, you need to think about what pre-solve is going to do, because we had a situation where we had a aggregated representation in the model. We decided to disaggregate it, and Gurobi, because we kept both of them in, Gurobi just recognized that the disaggregated part was dependent on the aggregated part and got rid of the disaggregations we did. So we had to I think turn off the dependent. No, we actually said, okay, let's remove the aggregated constraint because we only wanted the disaggregated ones.
Yeah, that hurts. I quickly wanted to give a shout out. So there's a question: is it possible to plot the curve of best feasible solution versus time, like you've shown us? Yes, it is, and Ed mentioned it. This is what's called the Gurobi log tools. So this is an open source tool. So I'm just going to bring that up real quick, just a second. So this is basically a way you can parse your Gurobi log files into pandas data frames, and then you can plot them using Plotly, and that's what we did here. And more than welcome, please check it out. And it's as I said, it's open source. You can just pip install Gurobi log tools, and off you go.
Yes, and we only scratched the surface of the kind of plots you can do.
Yeah. I mean, it's really so if you use Gurobi on a daily basis, then I think there is no reason for you not to have this tool on your laptop. It's and I don't say this as a Gurobi employee. I say this because it really cuts down. I mean, I read log files for a living. I get paid to do this, and I still prefer the plots. So that's because it just helps to show things and put things in perspective and compare and build more complex stories out of these. And this is, again, coming back to this tech talk, something you want to do. You want to visually explain something so that you can get a deeper understanding and finally find actionable items out of this.
Okay, I'd like to answer one now.
Go for it.
So is it possible that we miss out on the optimal solution by strengthening the constraints? And the answer is no. The rules for strengthening the constraints are that you are not allowed to do something that cuts off all optimal solutions. Now, there are two types of strengthening. There is globally valid based strengthening, where you only strengthen based on the feasible region specified by the constraints in your model. In that case, you miss out on no optimal solutions at all. But then there is this notion of dual-based strengthening, which we showed in the lot sizing example that I did, where you potentially cut off feasible solutions and could conceivably, although it was not illustrated in this example, but in other examples, it is totally legit to strengthen the formulation in ways that cut off some optimal solutions, but never all optimal solutions. And we can't deep dive into it now, but Gurobi's symmetry breaking functionality does precisely that. It actually can remove some optimal solutions from consideration, but never all optimal solutions. So I think that's all I need to say about that one.
That makes sense.
There's a question. It's an interesting one, and I imagine you both have thoughts. So, do you have examples of weak formulations where the lower bound quickly reaches the optimal value, but the incumbent is slow to converge?
Richard, do you want to go first, or shall I?
Sure, I've seen that. I mean, it happens. That's true. I mean, the main thing there is it's difficult to find the good solutions for whatever reason that may be. The main thing when you see this is you need to then zoom in onto how can you improve finding better solutions. The biggest weapon we have in Gurobi is heuristics. So you want to improve, turn up heuristics, investigate. Can you maybe use no-rel heuristic, which is something that's not used by default, and you can switch it on. So that would be my best guess. But absolutely, this happens. I wouldn't call that a weak formulation, though.
Yeah.
Linguistically
speaking, but that can happen totally.
Yeah, I have nothing to add. It's not with the true definition of weak formulation that we've been adhering to. That's not weak, but you definitely can have models that are challenging to solve that exhibit that behavior.
Another very quickly to explain it. So there was a question on, does strong formulations have anything to do with the deterministic nature of Gurobi? For my case, whenever I run them, I came up with different optimal solutions with the same objective function value. No, that's a strong. So when you have in different objective function value, different solutions for same objective function values, all those solutions are equivalent to Gurobi. Because what the question Gurobi is actually answering is, you have an objective function. This is how I quantifiably judge a solution to be better or worse. So if I think of Google Maps, if I drive to the right or to the left, both times it takes me 12 minutes to arrive. For Gurobi, this means these solutions are equivalent. You might have an emotional preference for one because it's a prettier route, but for as long as that's not recognized in the objective function to give it a higher value, Gurobi, or Google Maps for that matter, won't care. And so that has nothing to do with determinism. That has nothing to do with strong formulations. Something that we call degeneracy. Degeneracy is the notion of having multiple solutions for the same problem. And then there's ways to deal with this, and you can have orderings and all of this lexicographic stuff, and that's a very, very deep rabbit hole. But that has nothing to do necessarily with the determinism at its core. It has something to do with degeneracy, and so I would advise to you that you look into changing the objective function such that you more accurately represent what you actually want to get out. Sorry, guys, that was a little bit long.
That's okay. I have one that I'll try to respond to, although to truly answer it would take hours. But I think I'm going to try to refer the questioner to some resources. So what is the strong formulation to replace binary continuous variable multiplications? Like I said, I don't think we can answer that here. I'm not sure whether they're talking about separately products of binaries and products of continuous, but there are some Gurobi webinars on specialized strategies for products of binary variables. And there also are webinars and tech talks on products of continuous variables. But I don't think we can get started in the remaining few minutes we have to answer questions doing a deep dive on this one. So with that, let's move on.
There's a question about a scheduling problem. So a problem minimizing certain values in a scheduling problem. I don't quite understand it, but it's a weak formulation that they're running. Branch and Bound's offering a lot how to improve that. Any recommendations, articles? So
go ahead. Go ahead.
So scheduling, and if there's like a make span, minimizing time. So scheduling can often have two different types of formulations, binary variables that decide whether one activity happens before another. Another formulation is where you discretize time, saying does an activity start at certain time periods. And it really depends on a lot of things which one to go. And these are examples where you completely change the definition of variables, and you end up with different formulations and different strengths. That's something that we didn't really cover in our examples today. Some scheduling problems, this will happen. They'll inherently be weak, and it reminds me similar to the 2D plotting, 2D lapping problem box. What's it called? That you guys discussed last time? Bin packing.
Rectangle game.
Yeah, where some of these will inherently be difficult. In which case, maybe you just want good feasibles, and then going straight for heuristics is the way to go. So I'm not sure if there's any articles I can refer to off the top of my head. It really depends on the details of the scheduling problem. I'm sorry, unless Ed's got.
I have just two real brief things on this. Again, yeah, this is a topic that we can't really answer in 1 minute or 2 minutes. But yes, go watch the recording of part 1 of this tech talk. We have a little game that relates to these types of problems. And number 2 is just try aggressive lift and project cuts, which is a relatively new Gurobi feature. They are well suited to those conditions that you enforce to prevent overlap of the tasks. So those are 2 sort of broad suggestions. That's all I have to say. Steve gave a more detailed answer.
So we are almost half an hour over time. So I would like to answer the remaining 4 questions relatively quickly. I will take one of them. So I run into a MIP formulation with a routing problem with time windows, in which a change in objective function changes the branch and bound process a lot. Substitute minimize local en route time of all vehicles for minimizing total waiting time reduces the solving time from days to minutes and hours. I've been struggling to understand why. Do you have an insight for this? Well, it depends. Long story short, so routing problems are notoriously weak, because the formulation is just if you look at it, the LP MIP, what you call it, the difference between the 2 formulations, what they mean. The LP means you can just shoehorn everything together, and that's a problem. And so when you change the objective function, suddenly the LP relaxation might not have the desire to shoehorn everything together like when you have it in the on-round time. And so this is specifically for your model formulation, the way you created it, and for the data and the specific underlying network that you have at hand. Generally, it's a good idea. This is one of the things we didn't get to this, but changing the objective function, if you can, might be a good idea to strengthen the formulation. Because I had a case 2-3 months ago where I had a QP, I want to say 50 milliseconds, 100 millisecond solve times. I add a linear term, hours of solve time. So it has a huge effect. You just have to go for it and look at this disconnect between LP and MIP formulation. Okay, next one. Steve, pick a question.
There was a question about a large scale MIP problem, and then you have a bilinear term, and any suggestions how to solve it. I would say just add the bilinear term and try Gurobi's. So Gurobi can handle bilinear, so product of 2 continuous variables.
Yeah, but that's the McCormick relaxation, right? We use, or I guess.
But that's fine.
Okay.
Right?
I mean, they themselves apply the McCormick relaxation.
Yeah, okay. That's how I understood it.
Okay. Yes.
So we do it ourselves, and it seems to be super efficient. And we're looking for more problems. So if you'd like to do it and send it to us, we'd be interested.
Yeah, I mean, see how Gurobi handles the McCormick relaxation. One key thing about Gurobi in terms of its non-convex quadratic solver is it has a lot of good pre-solving reductions as well that I think probably if somebody tries to do it themselves, they're sort of likely to miss out on. So yeah, give Gurobi a shot. If it doesn't do it, yeah, and you're willing to share a model, we're always looking for more models so we can improve that solver.
Okay, two more. So Corey asked a question: do you have any recommendations for MIPS which consider equipment states on, off, startup, standby for minimization of operational cost? The formulation is basically a unit commitment problem, but with more than on-off states. These exact extra states are causing much higher runtimes. Without seeing the actual formulation, I don't really dare to say anything here. I don't know whether any of you, we have, so a colleague of mine, Rodrigo, he's a unit commitment expert, so he might actually be able to answer this one. But I know the unit commitment problem, but not to the extent that I would be able to answer this.
The only comment I have is one in general that might help, but doesn't relate to the specific extension that the questioner described, which is unit commitment style problems have time periods typically, and branching on the earlier time periods makes a lot of sense. Now, so it might be worth trying that. It may turn out that that is more important as you extend beyond the basic on-off states to those additional states like standby. I do think there is something that could be done there, but yeah, in 1 minute off the top of my head, I do think there would be ways. Again, my other recommendation is what we said today. All right, think about what the relaxation means. What does relaxing integrality mean, not only for the on-off states, but for the other states? And that's the first thing to get a handle on for tightening the formulation. So for this last one, I think I can answer it. I'm going to share my screen. And
so the last question, by the way, was why was the box on Ed's screen so tiny? In other words, what's the disconnect? Why were we able to say visually that the disconnect was meaning that this box was so tiny?
Right. So the point is that if you have this sum of these 7 U variables times 480 is greater than 3. When you relax integrality, all that means is, okay, this sum is now greater than or equal to 3 over 480. And there's a high cost on all these U variables that we're adding up. So the objective is going to make this equal to 3 over 480, not greater than or equal to 3 over 480. So the point is we can meet our demand, yet only operate at a fraction of the cost. So when I created this picture of a small machine, I'm viewing it in terms of the costs of operating this original machine is tiny. So equivalently, the machine itself is tiny. That's what I was trying to get across. Maybe I didn't articulate it as well as I could have, but hopefully I've now conveyed what I was trying to talk about there. So with that, I'm going to stop sharing. I noticed maybe you took care of it, Richard. Somebody asked about whether we were going to have donuts for everybody.
Yes, I suggested we have digital donuts for everybody that are floating around, ready to be served.
Yeah, I think the problem is, we're still working on that sort of transporter room kitchen box where you can transport food, from one person to another anywhere in the world. But we haven't got that working yet. But the other issue with that is that if we ever succeed in doing that, we're probably going to change our line of business completely and won't be doing tech talks on optimization anymore.
Who knows that? But we'll settle for digital cookies, exactly.
I guess so.
Yeah, the one thing I want to say though, speaking of digital donuts, physical donuts, one idea we floated around in the Tech Talk team is at some point, if it happens, to do a physical version of this, so actually to meet up and do an actual event where we do these live. This will definitely not happen this year, but at some point maybe this will come up. So then we will actually bring donuts as well, I promise. So with that, I want to say thanks to everybody who stayed. This is amazing to see so many people staying almost 40 minutes after the scheduled time. I hope we haven't wasted your time. And yeah, thanks everybody. We'll be back in around 3-4 months with the next one. If you have any ideas, please let us know in the feedback questionnaire that's going to be coming your way soon. And have a great rest of your day. Take care. Bye-bye.
Thanks, everyone.
Bye, everybody. Thanks.